The next exam, third exam, is a week from today. So I'll give you more details on Friday. Talk about it. So I'm going to do just one more power series example that I thought I had this all straight here. Okay. Okay, so let's try this. Okay, so here's a power series. What makes it a power series? Yeah, so it's like a function, right? It's a function of x. So depending on different values of x, this series may converge or not. And the question is, for what values of x does it converge and or not converge? So we know we use the ratio test, right? Ratio test means look at the limit of the ai plus first term over ai. So this is a new sequence based on that series, right? It's the sequence of ratios of the next term to the previous term. So we look at what, and that was like the multiplier, right? That's the multiplier from term to term. And so we're asking, what do those multipliers do? Do those multipliers approach a particular value that's less than 1? Then this series is becoming like a geometric series with an r less than 1, so it will converge. That's kind of the idea of this. Yeah?
I think you have an n inside the summation.
Oh, okay, thanks. No n's in that, right? This is all i's here. Okay, thank you. Are we good now?
Yeah.
Okay, so we've done lots of these, and I'm going to have what? Negative 1, I plus 1, I plus 1, x plus 5, I plus 1, 3 to the I plus 1, over 2 to the 2i plus 1, and then times 2 to 2i. So that's that big thing is just this ratio of the ai plus first term to the ai'th term for this particular series. So we're going to simplify that and see what that does in the long run. And that will tell us about the series becoming like a geometric series or not. Right? So I think we gather like stuff together. We'll have a negative 1. We'll have one more 3 on the top. How many more 2's do I have on the bottom versus the top? 2 more, so that's 4, right? 2 squared. How many more x plus 5's do I have and where? 1 more on the top or bottom? On the top. So I think we end up like this. Agree? Agree with the math? And we're asking what happens when I gets big, right? As I gets big, what happens to this? -1, absolute value of -1 goes away, right? What about I plus 1 over I? Goes to 1. What about 3/4 and x plus 5 as I gets big? Right? Those have nothing to do with I. They don't care about I. Right? They're just going to stay like this. So this was happening when I gets big. That ratio of I plus 1 to I goes to 1, and then we're left with 3/4 absolute value 3/4 x plus 5 as I. Okay, are in agreement? Yes? So what needs to happen for this series to converge then? In order for the series to converge, this thing must do what? Or must be? Less than 1, right? This is like R, right? It's like R in a geometric series. And so because it's like R, it needs to be less than 1 in order for it to converge. So then we get, what, 3/4 x plus 5 is, and this was the main reason I want to show this example, for this step right here. So that expression has to be between -1 and 1, but the question is what values of x make it converge, so that means we have to solve for x, right? We solve for x. First step in solving for x. Yep, so getting to the x here, the 3/4 comes first. So it's just like solving an equation. You just have kind of 3 sides to it rather than 2 sides. So we're going to multiply by 4/3. And then subtract how many thirds? Subtract 15/3, is that right? So you get -19/3 less than x less than -11/3. So our interval is going to be from -19/3 to -11/3. We know for all x values in between those, for sure this thing will converge. Now, your endpoints are values of x that will make this equal to 1. So then the ratio test is inconclusive. That's where, so when you get these endpoints, those endpoints will specifically make this equal to 1 or -1, meaning the limit is 1. So we need another test besides the ratio test to figure out the endpoints. So we'll plug -19/3 in and solve that as its own series. No more x anymore, right? That's just a straight up series. But you can't use the ratio test. And then -11/3, you'll put it in here, and you'll get some series. You need to simplify it and analyze that series, whether or not you're going to include equals or not on these. I'm not going to take the time to do that. And then, so the width of this interval is that -8/3? Or just 8/3, the width is a positive value. Just 8/3 from 11 to 19/3. So therefore the radius of convergence is 4/3. How far is it from the center out to the edge of this interval? It would be a length of 4/3, either way. Okay, questions on. So I mainly want to show you that for this last part, solving an inequality that's a little more complicated, but it's still stuff from old algebra stuff. Any questions on that one? I think so. Tonight at midnight, the Power Series online homework is due, and then the next online homework opens right after class at 3. In case you want to get started, you can get started on maybe like the first 4 or 5 of those after today's material. And then I made that due Tuesday at 5 p.m. so that you can be in review mode the night before the test. Okay, so that next, the one that opens today, Tuesday at 5, and I'll remind you of that. Any questions before we start the new topic? Yes, sir?
It's not entirely related, but when you divide by a negative for inequality,
Yeah, it'll flip
sign,
them.
right?
Yeah, that's the one thing that's different about solving inequalities from equalities. Whenever you multiply or divide by a negative number, it changes the direction of your inequalities. Other questions? Okay, let's talk about the new stuff here. So the new stuff is something that we call Taylor polynomials. So I'm going to give you like a kind of a visual tour of this so we know what we're doing when we get to the math. So here's a function sine x plus cosine x, and I've graphed it. And that's our function f. The idea of what's called a Taylor polynomial is it's a polynomial that will try to be like this graph, try to replicate or approximate this graph around a center point. So this is what we call the center. So I'm setting the center at a equals 3. So I'm gonna show you some Taylor polynomials for this function, sine x plus cosine x, centered at a equals 3. And so, and that's the x value. So here's 3 right here. And that's my value of a. So we know polynomials come in different degrees, okay? So a 0th degree polynomial is what kind of function? If it's 0th degree polynomial, then what's that function like, or what is that? Horizontal line, right? It's a constant, right? It's a constant. So if I wanted to pick a constant function that's trying to be like this function at x equals 3, what would that function be? What would that function be? A constant function that's trying to be like this curve. It obviously can't do a very good job, but so here's the point on the curve at x equals 3. So what will this constant function be like? What value will it have? If this is the function f, then what value will that constant function have? Yeah. F of 3, right? So if it's trying to be like the function at 3, then the only thing it can do is get the function value right. Does that make sense? So here's the 0th degree Taylor polynomial at x equals 3. Does it do a good job approximating the function? No, but it gets one thing right. What does it get right? It gets the value of the function at the center point, 3. Make sense? So what about so now if I wanted a 1st degree polynomial or a linear approximation, what would that be like at 3? So that would get the function value right, but what else would it get right? If it was a linear approximation. Slope, right? It would get the first derivative right. So here's what that would look like. So that's the 1st degree Taylor polynomial. It's a linear function that's trying to approximate this sinusoidal curve centered at 3. So it gets the function value right at 3, and it gets the slope right at 3. So what about so that's the 1st degree. What about the 2nd degree or quadratic polynomial? What kind of graph is a quadratic? Parabola, right? So a parabola will get the function value right, it'll get the first derivative right, and also second derivative right, and it will look like a parabola. Now notice what's happening now. So this is the quadratic approximation or 2nd degree polynomial. This is T2 or quadratic approximation. Does this do a good job of approximating the function? Where? What values? Does it do a good job approximating the function? Close to 3. It's like now there's like kind of an interval around 3. Do you see that? Where this quadratic function is kind of doing a good job of replicating that. But as soon as you get away from 3, it's terrible again. All right, 4th degree polynomial. Or sorry, 3rd degree, cubic. There's a cubic function that's trying to replicate this function. How is it doing replicating the function? compared to the last one? Better. Like there's like a wider range around 3 where it's kind of hovering close. But then as soon as you get again, away from 3, then it flies off, right? Here's the 4th degree. So this is the quartic polynomial trying to be like the function. So with higher and higher degree polynomials, you get better approximation for a wider range around 3 each time. Okay, so this is the idea behind Taylor polynomials. Trying to replicate the function with some degree polynomial. The lower the degree, it's gonna be right at 3, but then as soon as you get away from 3, it won't do a good job recreating the function. But higher degree polynomials do better and better replicating the function for a wider and wider interval around your center point. So just another quick example. I'll do another function in center point so you can see it. So how about 1 over x and at negative 1.5. Give it away. Okay, so at negative 1.5, we're right here. It's this point right here. So there's negative 1.5, so it's this point in the graph. So what will the 0th degree polynomial look like? Horizontal line through that point, right? So all it's going to get right, the only thing it's going to get right is the function value at negative 1.5. And then a linear approximation, or the 1st degree Taylor polynomial, will get that function value and slope, gets the first derivative. Quadratic function gets the first 2 derivatives and the function value. Cubic, first 3 derivatives. Quartic, first 4 derivatives and the function value. And then again, you see with each higher and higher degree polynomial, you're getting a wider and wider range. So here, for the quartic, it's pretty good, all the way from about 0.5 to 2.3 or something like that. So it's pretty decent there because it's. So then as soon as you get outside that range with the quartic polynomial, it doesn't do a good job anymore. Okay, so that's the idea behind this. So keep this in mind as we're doing the math. That's what we're after here. We're after creating these polynomials that are trying to replicate the function and about some center point. So just briefly, why? Why would we want this? Well, so polynomials are like kind of the easiest functions to work with. They're just based on pure arithmetic, right? Multiplication, powers of x, and addition, right? That's polynomials are just based on pure arithmetic, whereas other functions like exponential functions and sine and cosine, logarithmic functions, 1 over x, kind of like less user-friendly, less like easier, harder to work with sometimes, and so maybe you have a situation where, especially like taking derivatives and antiderivatives. Polynomials are the easiest ones because it's just power rule, right? So it offers a way to recreate a function with something that's easier to work with, a polynomial. Okay, so let's jump in here. So here's the form of any particular Taylor polynomial. I showed you the 0th degree and the 1st and the 2nd. But so the nth degree Taylor polynomial will look like this. So there's a slight difference between this and what you're used to for a polynomial. So here's what we typically write for when we're writing out a general form of a polynomial. So how is the version of a Taylor polynomial different than the typical version of a polynomial that we usually write out like this? What's different? What's different? If you look at each one of these. Instead of x, we have x minus a. What does that do? So if you subtract every x value by a, like think about the graph, what does that do to the graph of function if you subtract? It's a shift, right? It's a horizontal shift. So how far in which way? Remember? If you subtract from the independent variable, that shifts it to the right. Okay, so it shifts it to the right a units. And so that's the whole idea of centering, right? So we're taking the standard polynomial equation and we're going to shift it to the right a units so that it's centered on that focal a value. Okay, but then still, it's still just a polynomial. It's just shifted over. Okay. So really the only thing to write a Taylor polynomial, the x minus a to the power, that's set, right? That's not going to change. So what varies from function to function is going to be what the coefficients are. So we are looking for these c's, right? I'm going to highlight in green here. What are those? If we can get those values of c, then we, for a particular function f, then we have the Taylor polynomial that we want. So we're going to go through the math of how do we come up with those c's. All right, so we're going to figure out, first we're going to look at this as the general Taylor polynomial. And we're going to start with the easiest situation, which is we want our Taylor polynomial at a, what do we want that to equal? So if the value of our Taylor polynomial at a, we want it to equal what? F at a, right? Of course. So we want the value of our approximation to be the same as the value of the function at the center point. So according to the function, what is t of a? So t of a, according to our Taylor polynomial, equals what? What would happen if you evaluated t at a? What would you get? All of these would be what? At t of a. 0, right? You're going to plug a in for x, and all these are 0 except for c naught, right? So we want t of a to be f of a, and we know that t of a is c naught. What does that mean we need to do? How should we choose c naught so that t of a equals f of a? What is c naught? It has to equal what? Right? We want t of a to be f of a. According to our polynomial, it equals c naught. Therefore, we're going to make c naught what? It's so easy that you're just falling asleep, right? F of a, right? So I'm going to write that up here. We figured out what the first one was. Okay, so if I have the function natural log of 3x, say f is, we're doing natural log of 3x, centered at x equals 2. What's the constant term in our Taylor polynomial? I want to replicate the function ln of 3x centered at a equals 2. What am I going to make the constant value in my Taylor polynomial? Yeah.
Natural log of 6.
He wants natural log of 6. Agree with that? Yeah, it's f of a, right? What is f of a? F of a is going to be ln of 3 times 2. So that it'll be ln of 6. Do you see that? Okay. Oh, no, I want to keep that. That's the one thing I want to keep. So this is f of a. This one right now. All right, so now, in order to figure out what C1 is, that has to do with first derivative. So we're going to take the derivative of this. Well, that's just power rule, right? That's power rule. So so we're going to do one term at a time. What's the derivative of Cn x minus a to the n? What would the derivative be? Yeah, Tristan.
Cn times n times x minus a to the n minus 1.
Did you hear that? You're going to bring the n down in front and reduce the power by 1. And then we're going to do that the same on all these. Bring the power down, multiply in front, reduce by 1. And so it gets, the expression gets a little, little hairy, but a little ugly. But we know exactly what's going on there. We're just using the power rule. So there it is. N times C, n, x minus a to the n minus 1. Come down to here, we get 3 times c, 3x minus a squared. Bring the 2 down, etc. Okay, this is going to help us get what this is going to help us get what C1 is. What do I want the first derivative at a to be? So the first derivative of my Taylor polynomial, what do I want it to be? The first derivative of the function at a, right? So I'm trying to reproduce that function, and I'm going to get it perfect at a. I'm going to always get it perfect at a. So, but according to the first derivative of the function, what does ta equal? I'm going to put the 1 in there, okay? So 1c1. So I want the first derivative to be the first derivative of the actual function at a. According to the first derivative of my Taylor polynomial, it's equal to 1c1. Therefore, what should c1 be? So that the first derivative of my polynomial is the first derivative of the function. What do I want to make c1? What should it be? F prime, right? F prime of a. So for this little example, tell me what what will the figure out what that coefficient will be for this example up here. If I was replicating ln of 3x at a equals 2, find out what the c1 coefficient will be in that Taylor polynomial. Go, everyone do that. Figure that out. You're either making progress or you're getting help. Okay, someone got it? What do you think? Drew, did you get it?
I think it's 1/2.
He thinks it's 1/2. Others? And how'd you get that?
So f prime is 1 over x, because the 3 over 3x makes the 3 cancel.
Okay, so you get 1 over 3x, and then by the chain rule times 3. So it's 1 over x, and then?
And then plugging in 2 gives you 1/2.
Our a value is 2, so I get 1/2, right? So it would be 1/2 in this case. Okay, so we got the first two. And so what do you suppose C2 is? Second derivative at a, right? So, well, wait a sec, not so fast. Let's actually do the math and make sure. Okay, so now we're taking to work on the second coefficient. That has to do with, relates to the second derivative. So we're going to take the second derivative of our general form of the Taylor polynomial here. And we're going to use the power rule again. And again, don't let it scare you. It's just bringing the power down and then reducing the power by 1, right? That's the power rule. It's just kind of a long, little tedious equation. But there it is. And so now I want my second derivative at a to be what? What do I want the second derivative of my polynomial a to be? Second derivative of the function, right? Right? We want to get things right at a. We want to get here now we're to the second derivative. We want to get the second derivative right at a. We're going to have our polynomial give us the same second derivative as the original function. But according to the function, the second derivative of a equals what? 2 times 1 times C2. So, therefore, we need that to be the second derivative at a, which makes, so what should C2 be? so that the second derivative at a is the second derivative of our function. What should C2 be then? Second derivative of the function? Is that it? Over 2. Over 2 times 1. So now, I'm actually saying, what does C2 need to be? So this whole thing is my second derivative at a. It's going to be the second derivative at a divided by 2 times 1. It's kind of like solving for C2, right? So this is going to be the second derivative at a over 2 times 1. So it wasn't just the second derivative at a. Now when we get this power rule, repeated power rule over and over again, something else is happening. Okay, questions? Okay, and what was our first derivative? 1 over x, right? Turned out that the 3's went away. All right, so find what would our C2 be for this scenario? What would C2 be for the f of x is ln of 3x and it's centered at a equals 2? So what we found? C0 was ln of 6. C1 was 1/2. What would C2 be in this case? Got it? Tell me. Yeah? Negative 1/8? Agree? Because the derivative is negative 1/4, right? So if you take the derivative of that, you get negative 1 over x squared. So f of a would be negative 1/4, but then you have the divided by the 2 as well. So you get negative 1/8. Any questions so far? Is this making sense? Okay. Next one. We'll do one more. And then we'll have the pattern, and then we can just write the general term. One more derivative, third derivative. Third derivative is this. So again, we're just bringing the power down, reducing the power by 1 for every term. And so this is going to help us with the third derivative. So we want the third derivative at a to be. We want it to be. We want to get everything right that we can at the center point. So we want it to be the third derivative of the function at a. And according to the function, what is the third derivative at a? Yep, 3 times 2 times 1, C3. Because when you plug in a to all these, they're all 0. So what should C3 be? So we can make our third derivative of our polynomial be the same as the third derivative of the function. So what do we make C3 so that this is the third derivative? Yep.
Would it be f triple prime of a
Yep.
over 3 factorial?
Yeah, so you see the pattern. It's 3 times 2 times 1. This was 2 times 1. So yeah, it's 3 factorial. I'm going to change this now too. And actually, that same pattern was occurring before. We just didn't notice. This is. And this is 0 factorial, which is 1. So now we've got it. So the nth degree coefficient, what would it be? The nth degree coefficient, or any coefficient that you want, is the nth derivative evaluated at a over n factorial. And once you have the coefficients, you're done. You can write down any of the polynomials that you want, because it's always going to be x minus a to the first, x minus a squared, x minus a cubed. You just have to plug in your a value, right? You just have to get your a plugged in there. Okay, so now we have what we need to construct any Taylor polynomial for any function and any center point, because we know what the coefficients are. So this is the key right here. Okay, anybody have a question? Okay, let's try an example, see how you do. Can I erase this? So now we're going to look at, where's it? What do I do? Did I do this? This. There we go. So I got, now we're going to work on sine of 1/2 x. Sine of 1/2 x centered at a equals 1. So I want you to find the coefficients. So find the constant coefficient, the linear coefficient, quadratic coefficient, the cubic, and the quartic coefficient. And then once you have the coefficients, you're going to use those to write, we're going to write the first 4 polynomials. Or let's just actually, we'll just write, just start by writing, if you're confident on this, then just try T3 after doing this. What's that? That's the cubic approximation, or the 3rd degree Taylor polynomial of this function centered at 1. Okay, go. You're making progress or you're getting help? You're making progress or you're getting help? So our function is sine 1/2 x. Our center point is 1.
No, I was wrong. That should be over 3. It shouldn't be 4. I think 3 factorial is just 6. So yeah, it's 6. 16 over 6. 1/16 over 6.
This is what you should be using, right? This is what you're doing? That's what you're calculating, right? This is what we spent 20 minutes figuring out, what those coefficients are. So they're always this. But so now we got our function f and our a value of 1. So you're figuring out what those are for our situation now, right? Okay, so we're going to need the derivatives, right? First derivative is 1/2 cosine 1/2 x, right? Did you find that? Second derivative is negative 1/4 sine of 1/2 x. Third derivative, negative 1/8 cosine 1/2 x. And fourth derivative, is it positive 1/16? Do I got those right? Did I make any mistakes? Right, because these are all based on, each one is based on a derivative, right? Evaluated at a divided by the n factorial. Okay, so what is C0? So what is our first coefficient? It's f of a, right? F of a is sine of 1/2, right? X equals 1. So first coefficient, 1/2 cosine of 1/2, and then divided by 1 factorial. That just is just 1. All right. Second coefficient, Let's have someone tell me. Who can tell me what that is? Logan, did you get it? Negative 1/4. Sine of 1/2. Over 2. 2 factorial. So then that could be negative 1/8, right? That's negative 1/8. All right, third one. Somebody else? Freddie, did you get this one? Did you get the third coefficient?
No, I didn't.
Okay. Chance, did you get it?
Yeah, I think so. It'd be the third one negative cosine 1/2 over 8 times 3 factorial.
Yep. So negative, that's right. Negative 1/8 cosine of 1/2, all divided by 3 factorial. And then finally 1/16. And it's just 1/2. Why? Because our center is 1. So we're plugging 1 in for the x value, right? F of A, F prime of A, F double prime of A. That means evaluate at A. Plug the A in. Okay, so then what is T3? What is the third degree polynomial then? Start with? So let's actually simplify this. Negative 1/8 and 3 factorial will give negative 1. 3 factorial is 6, right? So negative 1 over 48. Cosine 1/2 times what? X minus 1 cubed, right? There's the cubic. We got the coefficient. We know it's going to be times the x minus a. A is 1 cubed. Then, is it negative 1/8? Times sine of 1/2. Oh my gosh. Whew. That was a close one. So 1/8 times negative 1/8 times sine of 1/2 times x minus 1 squared. Then C1 is plus 1/2 cosine of 1/2 times x minus 1 plus sine of 1/2. So that's the third degree Taylor polynomial. And it serves as a cubic approximation to that function centered at 1. Right? So it's a cubic approximation centered at 1. So when you have the different Taylor polynomials for the same function and center point, the coefficients don't change. Right? So if you were to do the linear approximation, it's the same coefficient. It doesn't change when you get to the T1. So this, what I'm circling in orange right here, that's T1. Right? It's just the linear term and the constant term. And then T2 would then include that one. So within a particular situation, function, and center point, C2, the coefficient C2 is the same for all the Taylor polynomials. C3 is the same for all the Taylor polynomials. So every Taylor polynomial has in it all the previous Taylor polynomials. Just like this is a T1, include that one as T2, include the cubic as C3. So let's look at them. So let's graph the one that I said. N equals, what's the one we did? N equals 3. Looks like that. So that's a cubic function that's centered at 1, that's trying to be like sine of 1/2 x as best as it can. And it's doing a really good job for this interval around 1, right? And at 1, what does it get correct? So at x equals 1, what's correct about this Taylor polynomial? Function value? and the first three derivatives are all right. And that's why you get a range where it's close around it then. Okay.